We feel lost. We're on this island of now all the time. We don't feel these connections with the past, and we can't envision the future either. So we're just kind of isolated.
This episode of the Rise Up Midwest podcast features Marsha Bjornrud, a professor of geology and environmental studies at Lawrence University in Appleton, Wisconsin. Professor Bjornrud was joined by Nick and Amanda from the Midwest Renewable Energy Association, who ask her about how geology informs our current moment and about Bjornrud's book, Timefulness, How Thinking Like a Geologist Can Help Save the World. The book is available now at Princeton University Press. Bjornrud will be keynoting at the MREA's member celebration, June 26, 2021. For tickets and information about that event, visit midwestrenew.org.
Marsha, hello,
Hi.
welcome. Thanks for joining us.
It's a pleasure.
Yeah, we appreciate you making the time. Let's start with the most important question. How do you pronounce your last name?
It's Bjornrud.
Bjornrud.
Yeah, just like it's spelled. I thought maybe you were Scandinavian. Do you have Scandinavian background? Or
Hyla, my dad says it's Polish.
okay, because in Norwegian, hylla means like a ledge or a shelf.
Oh, interesting. Yeah, that's
But,
why when I Google my last name, it's just a bunch of shelf pictures.
And maybe it's an IKEA word that
Well, I am Nick Hyla, Nick Shelf, I guess, from the Midwest Renewable Energy Association, and joining me is...
Hello, Marsha. My name is Amanda Schennebeck. I am a program manager here at the MREA as well. And for what it's worth, my last name Schennebeck is German adjacent, or it used to be German at one point before we Americanized it a lot. And it means something to the effect of the shining brook or the reflection off of the water. Shinen is the verb that means to shine.
That's much more beautiful than shelf. Well, thank you for joining us today, Marsha. We know that you're quite busy as a professor of geology, and I guess I'll start with my first question. You have the privilege of teaching this new crop of young minds. Should we be optimistic?
Absolutely. I feel like we're at some sort of inflection point. I think it was happening before the pandemic, but I think for all the travails the pandemic has caused, it's possibly catalyzed a moment of change. And I think although this year has taken a toll on students and everybody for various reasons, it's been a moment for reflection, for reassessment, for realigning our priorities. And I am optimistic. I feel like we're at a moment where the opportunity and the will are converging for real change.
I'm wondering, Marsha, if you could tell us a little bit more about how you specifically got into geology, and then also how you've worked to change how it's taught and how it's focused on in academia.
Yeah, one of the reasons I have begun writing more for probably popular audiences is the shocking lack of awareness and understanding by most earthlings about how their planet works, and really through no fault of their own. It's simply because geology, for historical reasons, just did not get included in high school science curricula at the time that those became codified, probably in the early decades of the 20th century. Physics, chemistry, and biology were already fairly mature sciences. And frankly, the earth sciences were lagging behind at that point. And so it's just a historic artifact that people are not exposed to geology. And in my view, that's a source of so many of the environmental problems we have. People in positions of power in business, in government, have shockingly little understanding of what they're actually governing when they're making major decisions about climate, energy, water resources. They're going in almost blind. And I was the same. I had very little background in the earth sciences in public schools. I had reasonably good public school education here in Wisconsin, but really never encountered geology until I was a freshman in college, where I took it, frankly, to fulfill a general education requirement in a lab science. And it was a revelation to me. It was really the etymology of the whole world. I was always fascinated with word origins, how words came down to us from previous cultures. And I saw that geology was really gave that sort of explanatory backstory to the earth and local landscapes, regional landscapes, everything. So I was hooked. It just made the world make sense. And so I'm a bit of an evangelist for geologic storytelling, because I think many people crave this kind of connection to place, trying to understand how things came to be the way they are. There are practical reasons as well, ranging from groundwater to climate change to soil conservation. There are all kinds of reasons we need to understand the way the planet works and its intrinsic timescales. So too many Earthlings walk around like bad tourists, frankly. They enjoy all the amenities of the planet, but have never had the opportunity or the inclination to learn its culture and language. And so my writing is an invitation for people who haven't had that opportunity to sort of jump in and feel their status as Earthlings.
Well, great. Speaking of your writing, your book, Timefulness, How Thinking Like a Geologist Can Help Save the World. It's a wonderful, wonderful book. I thoroughly enjoyed it. Maybe I'll just help you dig in a little bit to help us understand geology. You quote in your book, "Early in an introductory geology course, one begins to understand that rocks are not nouns, but verbs." Tell us what you mean.
I mean just that to me, a rock is not just an inert object. It embodies a story and a process. Rocks weren't here from the very beginning. They came into being via some process. And so becoming a geologist is reading the landscape as a narrative of the Earth's evolution. And I think that's the way to bring people into the field is making these things have agency, making them actors, protagonists in Earth's story, rather than inert and irrelevant artifacts of an impossibly distant past. So I really feel that when I was up in Duluth this weekend, first time in a long time getting out of town, and there are on the shores right in town are beautiful lavas that were laid down 1 billion years ago when North America nearly rifted in half. And to me, I can, in my mind's eye, looking at those rocks, I can envision these lava flows flowing over the landscape. They're still present in some way with us and speak to us of the processes by which they formed.
So I'm going to take us in a little bit different of a direction here, I think. But I read in your bio, Marsha, that you left Miami University in Ohio to return back here to Wisconsin. Was there something geologically speaking that drew you back to the state?
That's very perceptive. It really was, in part, the rocks. And in particular, the really old and complicated rocks we have in the northern part of Wisconsin and the Upper Peninsula of Michigan, which still have many mysteries and are a really wonderful opportunity for undergraduates in particular to get involved with primary research. And it was also winter. Frankly, Southern Ohio doesn't have much snow. And that was unfortunate for me anyway. So a variety of things, the people, the rocks, the climate, maybe all of them are shaped by each other.
You're listening to the Rise Up Midwest podcast. We'll get back to the podcast after this short sponsor break. Gimme Shelter Construction specializes in the design and construction of high-performance homes, including passive solar design, integrated renewable energy systems, sustainable materials, and the design and installation of masonry heaters. Gimme Shelter's creative blend of energy-efficient, high-performance homes and artful design sets them apart from other builders. Respecting the Earth's resources is a commitment they share with their clients and crew. Shelter from the storm, a source of inspiration, a healthy haven. Your home should be all of these things. Gimme Shelter's vision of thoughtful design, fine craftsmanship, and sustainability will ensure that it is. Learn more at gimmeshelteronline.com. And now, back to the podcast.
We'll skip away from Wisconsin for a bit and ask you to kind of start to take the past and the present, bring them together. Again, in your book and in your presentations, you talk about the cautionary tales of the rock record. Would you give us a few examples?
Well, let me say first that in the main, Earth has been a stable and hospitable planet. But once in a while, things have gone really badly wrong. And most of the time when things have gone wrong in mass extinction events, say, it's not something we can blame on an asteroid. There's really only one case where that's been well shown, and that's the dinosaur extinction event. But there are 5 great mass extinctions that have happened since about 500 million years ago. Of those 5, the dinosaur extinction is only the 4th worst. And the first 3 were times when the great, wonderful biogeochemical cycles on Earth that involve the water cycle and the carbon cycle, phosphorus, nitrogen, sulfur, all of these things playing together over long periods of time somehow went badly haywire for different reasons. And to me, the most sobering one is the End Permian Extinction. It happened about 250 million years ago. This was before the dinosaurs. And it is the worst mass extinction event. People were obviously not around. But the constellation of things that happened is eerily similar in some ways to things that are happening today. So it seems to have been triggered by an unusually prolific lava flow event in Siberia. We call the rocks that record that event the Siberian Traps. That's an old word for basalt. But huge amounts of basalt being extruded in a short period of time, and more importantly, for the climate, lots of CO2 being put into the atmosphere by those volcanic eruptions. And then that seems to have triggered some cascading effects on ecosystems that led to ocean anoxia and ocean acidification, both issues to us in the Anthropocene, to ozone destruction that was probably related to some of the volcanic gases. It played out over a period of probably several tens of thousands of years, but in the end, there was devastation in both marine and land-based ecosystems. We know the marine record better because there's a better fossil record. Something like 95% of all marine species went extinct. And on land, it was probably equally severe, but again, the fossil record on land is never as high fidelity in a sense. It was bad. And even more sobering is that it took something on the order of 5 or more million years for the biosphere to really kind of reestablish itself, and entirely new ecosystems had to invent themselves. In some ways, we're still living in the post-apocalyptic time of the Permian extinction, because it was the time when modern marine ecosystems in particular got established. The things like the trilobites and all of the Paleozoic organisms were really vanquished in that event, and a completely new set of characters arose. So the good news is life was not extinguished, eventually did thrive again. The sobering news is how long it took for life both on land and in the seas to recover.
Yeah, it really stuck out to me that we can only really blame one of those mass extinctions on a meteor. Is that correct?
Yeah, it's fascinating to me. I've been in the field long enough to see ideas about these mass extinction events evolve. And I think that there's something really appealing about the asteroid, finding an asteroid to blame, because it's terrifying. And there have been a bunch of movies about, that idea that what would we do if a large space object were hurtling toward Earth? But in some ways, it's a neater, tidier explanation, and it's not our fault. And so I find it fascinating how we sort of project our fears onto the screen of these mass extinction events, and how theories about what happened in the past do in some way often track things that we're worrying about. So the dinosaur extinction event, for example, and the idea of why that asteroid would have been so devastating came about at around the same time in the late Cold War era, where people were worrying about nuclear winter, which is still something we might perhaps worry about. But the scientific work on nuclear winter allowed people to envision this large magnitude natural event that might have been something like it. So there's this interesting, I think, almost subliminal parallelism between thinking about these mass extinctions and our own anxieties of any given moment. And I'm not denigrating the science. It's just that we have as time goes on, we envision more ways the world could end. The world as we know it could end, I suppose.
Marsha, I'm really interested in the beginnings of geology as a field. So I was wondering if you could take us back a little bit to that very start of geology and then the age of the Earth as well. So I found it really interesting in your book how you were talking about James Hutton's theory of the Earth, which came out in 1795, kind of as the start of the field, and then the connections that this has to Darwin's conclusions on the origin of the species. Can you explain some of those connections and maybe touch on what some of the process was like for the wider human population to gradually, begin to accept that the Earth was extremely old and not the 6,000 years that was previously believed?
Yeah, I'm really fascinated by that sort of late Enlightenment time, the end of the 18th century, early 19th century. There was a brief moment when geology was the science that was capturing the public imagination in the way that sort of space does now. And it started with James Hutton, as you mentioned. He was a Scottish polymath. I mean, geology really did not exist at that point, but he was a natural philosopher on the fringes of the Edinburgh Enlightenment. Edinburgh in Scotland at that time was second only to Paris, really, as kind of one of the centers of intellectual foment. So he was friends, dining and drinking companions with people like the philosopher Hume, the inventor James Watt. I think Ben Franklin actually visited Hutton once. Someone told me that at a talk I gave. So he was known, he was kind of a public intellectual, but he was also quite a poetic thinker. And he is usually credited with discovering deep time by being able to read a certain outcrop in the coast of Scotland near the border with England. But he had a background in medicine, and he really used interesting sort of organic metaphors for the way the Earth behaves, seeing it as a kind of superorganism, almost a version of the Gaia hypothesis, if people know about that the Earth is in some way a self-regulating superorganism. And then at about the same time, or a little after Hutton was humbled, I don't really mention him in the book, but he was, I think, in many ways a kind of kindred spirit to Hutton, seeing the whole fabric of nature and seeing it in this very holistic way that became unfashionable by the mid to late 19th century. And then there was Charles Lyell, who wrote the first kind of treatise in geology and formulating the methods of geology. And his book called Principles of Geology was one of the few books that Darwin had on the voyage of the Beagle, and was hugely influential on Darwin's thinking about how incremental processes could accrue over time to result in very large changes in the biosphere. So I think of Hutton and Humboldt and Lyell and Darwin as this amazing group who really didn't overlap much. Only Darwin and Lyell were people who were in communication with each other. And I wistfully think about how differently our science and science in general might have unfolded if the very whole cloth approach of those people had really gained traction. But what happened, unfortunately, was physics, which has a very different way of investigating the world and a very powerful one, reductionism, taking tiny little slices of things and investigating them, really was on the ascendancy. And the great physicist of the 19th century, Lord Kelvin, William Thomson, crossed swords with Darwin and basically asserted to geologists that their belief in an Earth that was hundreds of millions of years old or older was misfounded. And he was a very impressive person who did virtuosic mathematical calculations that geologists just couldn't refute. And that set geology back for almost a century. Geology became kind of it just cowered in a corner almost. It became very descriptive. Nobody was trying to spin these great hypotheses in the way that Hutton and Humboldt and Lyell and Darwin had. And in fact, it retreated to its own detriment from other sciences. Some geologists actually suggested that somehow the science of physics and the science of geology were incommensurate with each other. So geologists stopped taking courses in physics and chemistry. And so that really set geology back almost a century. And it wasn't until plate tectonics was discovered in the 1960s that we finally found our footing and had a a comprehensive theory of the Earth, which was what these early thinkers were looking for, but it was just too premature. They just didn't have enough information. But I do think it's a tragedy that Earth science is just not viewed as a rigorous field. We are in a golden age in the Earth sciences now, and people don't really appreciate that. It still has a kind of 19th century musty reputation.
Yeah, you write, which I thought was very revealing in some ways, that when you look at other scientific fields like mathematics and biochemistry and others, that most of the time the breakthrough researchers are very young, and most discoveries are made by younger, very ambitious folks. But in geology, we tend to buck that trend, and you see discoveries made by much older professionals. So why do you think that is?
I think you just have to be exposed to the wide array of Earth processes to really start understanding them. And I mean, it's geological. It accrues over time. And the Earth is big and it's close and it's hard to see clearly. And you just have to keep encountering things over and over. And I often use linguistic metaphors. It's like learning a language. You can learn the rudiments, you can communicate, the basics, but to learn the real idioms and to pass as a native speaker may take years and years. So I think that's just the fact. The Earth is complicated, and we don't have sort of idealized systems that no all electrons are the same. So physicists don't have to differentiate between particular instances of electrons, whereas two examples of sandstone can actually look quite different from each other. So it's just developing this sense of proportion and depth of field and a sense for the variety of things, and that takes time.
I think this kind of connects to something that you mentioned at the very end of your book. You say that while other senses may be dulled with age, the sense of time, which can be developed only by experiencing it, is heightened. And that's very clearly true. As someone with just over 3 decades under my belt on this earth, it's staggering to me how much has changed just in those 3 decades, specifically in terms of climate. So this also ties into time literacy and learning to think like a planet, concepts that you discuss a lot in your book. Can you touch on what those concepts mean for us and then provide some advice? Other than getting an advanced degree or career in geology, what are some ways that we can overcome this restraint in our mentality and learn to think like a planet and learn to have some time literacy?
Wow. Yeah. Good questions. And I don't think everyone needs to become a geologist, but I do think everybody needs to become better earthlings. As I said, citizens of a planet that's complicated and changeable, even in human kinds of timescales. So I think, first of all, developing a sense of what I call temporal proportion is important. Knowing something about the intrinsic timescales of different processes, especially the ones that can unfold on something like human timescales. I know in the Central Sands region, for example, groundwater quality and quantity is a big deal. And our problems with groundwater in that part of the state have arisen largely from ignorance about how the groundwater system works and how quickly we can alter it to our own detriment. So, groundwater, especially shallow groundwater, operates on kind of decade timescales. Those are very familiar timescales. Other things may be longer. And I think one irony with our climate crisis is that geologists for years, because we've always had to be vigilant to guard against young Earth creationism and the idea that the Earth is 6,000 years old, we've emphasized for a long time how old the Earth is and how slowly geologic changes accrue. In the main, that's true. But now we're trying to say that actually sometimes geologic change can be fast. And that's also true. They're both true. Earth has different tempos or tempi. And that's just, a more complex idea. So I think understanding how quickly climate has changed in the past, how quickly systems can change in the past, that's a responsibility of anybody who lives on this planet and is using the resources of the planet and enjoying its hospitality. On a more personal level, I know I feel actual existential comfort in knowing the story of the planet. Many people, I mean, the reason that so many people don't like Darwin's theory of evolution is it seems as existentially threatening to them. And that's one reason that geology was set back for such a long time. But I think if people actually begin to learn these stories and see that we have kin throughout all of the biosphere, and indeed in even the non-animate parts of the natural world, that is a real source of solace and connection. And I think it's something that can repair us in spiritual ways as well as in environmental ways. And that's a bit of a stretch, I know, for some people. Like, I don't think rocks do that for me. But for me, I honestly feel this deep sense of connection and rootedness that makes me less fearful of my own finite time.
You're listening to the Rise Up Midwest podcast. We'll get back to the podcast after this short sponsor break. The Panasonic Total Home Energy System doesn't just deliver clean power, it delivers peace of mind, thanks to long-lasting performance, battery storage you can depend on, and a full system warranty. Let's take your solar business to profitable new levels together. Panasonic, one system, one warranty, one partner, with trust built in. To become an authorized Panasonic installer or a certified Evervolt installer, contact your Panasonic regional sales manager and get started today. And now, back to the podcast.
One of the things that you started to talk about was the climate crisis. And here we sit enjoying our fourth atmosphere, right? As far as we know, this is about our fourth. I think we like it. It's a good one. It's a good atmosphere. However, right now, we are currently outgassing at about over a factor of 100 compared to volcanoes and other Earth outgassing processes. And there's this debate. And I think you and I, at least from what I can tell, what I've read, and from what I've heard you discuss publicly, tend to see eye to eye on this concept of geoengineering and some of the pitfalls. So maybe you could talk with us about some of the solutions that are being discussed out there to like the techno-optimism of solving the climate crisis without changing behavior, and maybe your perspective on the way forward.
Yeah. So we are at a stage where we probably, even if we are able to curb emissions drastically, we're still going to be in bad condition. Okay. So that's kind of the background to some of the geoengineering schemes. I'll start with the worst one, and then we can go to better ones. And the worst, I think, and the most dangerous, and the one that we could actually start now, and that's terrifying, is stratospheric sulfate injection. This is inspired by the eruption of Mount Pinatubo in the Philippines in 1991, which spewed, I think, something like 20 teragrams of SO2, that's a lot, into the upper stratosphere. And that stuff, very fine particles of very reflective sulfur dioxide, hung around in the upper atmosphere, the stratosphere, for several years, and did have a slight cooling effect on the planet. And this has been modeled subsequently. It eventually fell out of the atmosphere in a diffuse way, and the warming that had been happening kind of resumed after that. So people have begun to suggest that maybe we could replicate some of these large volcanic eruptions by injecting sulfate aerosols, very fine particles that are like little tiny mirrors in the upper atmosphere and reflect sunlight back. This is a slippery slope to hell for a variety of reasons, I think. And I think many geoscientists agree that it would not change the CO2 content of the atmosphere. If we continued to emit at the current level, it would be masking the underlying problem of more CO2 in the atmosphere. It would also be something that you're kind of locked into once you begin, because you'd have to continue to inject more and more because it does fall out. But then if you stopped after doing it for maybe 5 years or 10 years, you'd have this huge catch-up warming effect from the continued accrual of CO2 in the atmosphere that would probably be much worse for the biosphere than any more gradual warming would have been. You would not stop the ocean acidification process, which is really threatening ocean primary producers, because the CO2 content of the atmosphere is not only warming the planet, a lot of it's being absorbed by the oceans and acidifying the oceans. So that would go on unmitigated. And in fact, as the sulfur dioxide falls out of the atmosphere, that too could contribute to ocean acidification. The day-night differences would be different because this reflectivity of the sulfate particles only works during the day or during the summer, if you're talking about the high Arctic or Antarctic regions. So you'd be doing subtle changes to the differential between day and night and winter-summer temperatures that would wreak havoc with the climate system in ways we don't fully understand. We can look at what happened with Mount Pinatubo, but that was just a one injection thing that then dissipated again. We don't have a good sense of what the global climate and weather implications would be. Some models suggest it could perturb the Himalayan monsoon, the South Asian monsoon, on which many people depend for food production. And last but not least, we have no international governance mechanism to regulate this. So it's terrifying. And it's very controversial among geoscientists. Sadly, last week in Nature, the international science magazine Nature, there was an editorial advocating for more research into so-called solar radiation management, which is a terrifyingly bureaucratic way to describe this. Arguing that it's better to know than not know what the consequences might be. But many geoscientists just feel like the further we go down that road, the more inevitable it almost seems that it's going to happen. And sadly, it's cheap. It's actually technologically feasible now. Many people who were climate deniers are suddenly glomming onto solar radiation management after denying there was a problem, just saying, oh, we can fix it with this. So that's sinister and terrifying.
Yeah, very good answer. I think it demonstrates the complexity of the systems we're dealing with and the lack of an easy solution. And maybe as a follow-up, and I think it's pretty indicative of this because we see this across many different disciplines. For example, medicine, the rise of the microbiome. And so you write of the Mycrocracy in geology and its historical and present significance. Do you want to talk about that?
Yeah, I made up that word, I guess. I don't know if anyone else is saying. The Mycrocracy is rule by the tiny. And it can be used in a general sense to highlight the role of the small and incremental in accruing large changes, or more literally, that microbiota are in charge and always have been. Fungi, bacteria, archaea, zooplankton, phytoplankton, really they are the survivors. They're the earthlings that have been here since 3.8 billion years or longer. They've come through all the mass extinction events. They mediate the chemistry of the oceans and the atmosphere and us and govern our food and everything. They're in charge. We have the illusion that we're in charge. And yeah, the hubris is the word that just always comes to me, of thinking, for example, we could terraform another planet in some imaginable human period of time, stems from just immense ignorance of the complexity of this planet and how all of these ecosystem services have come to be over time. And in particular, just the amazing and still largely unknown world of microbes. We just have no idea. I'm actually reading right now Merlin Sheldrake's wonderful book, Entangled Life, about fungi. Completely alien life forms among us that are hugely important to, again, agriculture, everything. and just, it takes my breath away when people like, for example, Elon Musk, blithely suggest that, oh, we'll just set up another human colony somewhere else. They have no idea. I like, okay, go be Martians. That's fine with me.
Marsha, thank you so much for joining us today. A reminder to everyone listening that you can see Marsha give an in-person keynote Saturday, June 26th at the MREA Member Celebration in Custer, Wisconsin. For details and ticket information, please visit midwestrenew.org. And you can also find Marsha's book, Timefulness, How Thinking Like a Geologist Can Help Save the World, now at Princeton University Press. Marsha, before we let you go, is there any final optimistic thought that you'd like to leave our listeners with today?
When people tell me that thinking about geologic time is in some ways alienating to them, I often call to mind a teaching from a rabbi from the 18th century, Polish rabbi Simcha Bunim, who often would say that you should always have two slips of paper in your pocket. In your left pocket, one that says, I am ashes and dust, and one in the right that says, the world was made for me. And both are true all the time, every day. And if you can hold both those thoughts in your mind, I think you can live peaceably as an earthling.
This Rise Up podcast was hosted by Nick Hyla and Amanda Schennebeck. Editing and sponsor copy read by Matthew Brown. Led by the Midwest Renewable Energy Association, Rise Up Midwest is a coalition of individuals, businesses, and organizations working to build support for common sense clean energy policy and market development. For past episodes and to sign up for new episode alerts, visit riseupmidwest.org. The Rise Up podcast is provided for educational purposes. Views expressed by guests and MREA employees are their own and do not imply endorsement by the Rise Up Midwest Coalition or the MREA.